So let me go ahead and further and start with Nate Gemelke from Penn State, who will talk about topologically ordered gases called atoms.
Okay, so thank you very much. It's a pleasure to be here.
There's a microphone which is not necessarily for the audience in your room, but rather for the.
So I think, like Chris said, this is a great opportunity for a lot of different minds to come together with a lot of different viewpoints. And so today I'm going to start out with talking about how to create topological order in gases of cold atoms. And so I'll be talking entirely today about cold atoms. And so the work that I'll be talking about today in the last half is primarily done by these graduate students in my lab. Actually, this is not a graduate student in my lab. Anybody recognize who this is? You know, it's Lev Landau. Actually, Renee looks a lot like Lev Landau. So. Okay, so since I have the distinct honor of starting us out, I get to ask the very simple and straightforward questions. And so one of the things I want to ask is what are and why do we want to study fractional Hall systems? And so I think everybody knows that the microscopic mechanisms behind fractional Hall effects is a dynamical coupling of some kind of topological defect or a gauge defect and particles in the system. And so for a fluid, like a superfluid, an atomic gas superfluid, we would say that these gauge defects are vortices, and so there's some kind of binding between the particles and the vortices in the gas. And so I'll give you a very clear idea of what that means in just a minute. But this means that the energy and the dynamic timescales for binding these two things together are a property of the fluid. Okay? And that's something that, in a sense, is up to the fluid itself to determine for us. And of course, we know that these have macroscopic outgrowths that are pretty familiar by now. We have things like transport, Hall resistivities that are familiar from fractional Hall systems and electron gas. But we also know that other things are exciting here too. We have non-local order parameters. This is non-Landau-Ginzburg order. It means that this idea of Wilson or Kadenoff renormalization is a little bit hard to apply to these systems because they have long-range gauge potentials and emergent order in them. We also know that they have excitations with fractionalized charge and mass. And so one of the big goals for us is to try to do experiments that look something like this in a two-dimensional system, to take two excitations around each other and detect these fractional exchange statistics. Okay, and then also we know that they exhibit interesting signatures in entanglement entropies and spectra. So for all those reasons, these things are exciting to look at. And I want to give you just a basic idea of the flavor of these states. Probably most of you know these kinds of states look like this, but here is a half-Laughlin state. So this is a bosonic fractional Hall state. I'm going to be talking about bosonic atoms. And so we would write the n-body wave function if we use complex coordinates in a two-dimensional system where we take x and we add I, y to it. Then we would write the wave function something like this. It's some kind of polynomial. Here it's the second order because we have even exchange statistics or bosonic exchange statistics. And this would be a half-Laughlin state that has a total angular momentum of the particle number times the particle number minus 1. Now, we know that the local pair correlation in a state like this is 0. You can see that if two particles come to the same position, that this wave function will actually go to 0. So a good way of looking at this is to take this wave function and peg the position of, say, 3 of these particles and look at the wave function for the remaining particle. What you see if you do that is that there's a vortex in the phase of that remaining particle pinned at the location of each of those particles that you put down. So that's the flavor of the state that we're looking for. Okay. And of course, there are other kinds of states that are a little bit like this, share a similarity to this. So this is a 4-particle single vortex state. And so this looks a little bit like this in the sense that there's a polynomial here, but what you see in this case is that every particle in the system is spinning around the center of mass of the system. Okay? So there's correlation in that wave function as well. Okay, so there are different recipes that you could imagine for trying to produce these things in cold atomic gases. And the first one that I want to talk about is adiabatic production. And so really, I think to some extent, the bulk of the cold atom approaches are like this. And I'm going to talk about one in the first half of this talk that is an adiabatic production scheme. And the recipe here is to apply your favorite gauge potential. I'm not going to make a big deal out of what the gauge potential is. I'm going to happen to use the oldest one in our toolkit for neutral atoms, which is rotation. And we need to find some way to introduce vorticity. And then step 3 would be to introduce more vorticity. And then step 4 would be to repeat steps 2 and 3 until your vorticity is equal to your particle number, or comparable to your particle number. And there's some drawbacks to this kind of scheme because vorticity enters superfluids typically from the boundaries. Okay? And so vortex nucleation, as we know it, typically is a dynamic instability, which is to say it's not a coherent process. And so there's some amount of thermal effect every time we nucleate one of these vortices in a large gas. And at the same time, each of those vortex nucleations reduces the mean field energy a little bit, and it diminishes the subsequent gap to the next vortex nucleation. So this is a difficult game to win. There's another way of going about it, which is to use some kind of dissipation. So again, we can apply our favorite gauge potential, but this time we can also apply our favorite cooling scheme. And for cold atom physicists, this is usually evaporation. And so again, we introduce vorticity, more vorticity, and try not to cool it away as we're cooling the sample at the same time. And we repeat these steps again until our vorticity is equal to our particle number. And so there are very heroic experiments that have gotten on the order of hundreds of vortices in a typical Bose-Einstein condensate that has about 10,000 atoms or so. And so these are very difficult experiments to do. And at the same time, our filling factor is pretty far away from this idea of having one vortex for every particle in the system. Now, I like this scheme of rotation. There are a lot of different ways of applying gauge potentials that will do these kinds of things, but I want to talk about rotation. And the idea here is that we are going to put atoms into a two-dimensional harmonic trap and then rotate it. And if we think about what happens to the momentum when we do that, we see that we can write some kind of Hamiltonian for the atoms in the lowest Landau level, which is basically a kinetic energy that tells us how far away we are from the centrifugal limit, where our rotation rate of the frame is equal to our trap frequency. And then another term, which is just the contact interaction between the atoms. And typically we take this as being repulsive. And so our strategy here is actually not to work with 10,000 atoms, but to work more like with 10 atoms. And what that allows us to do is increase the trap frequencies using tricks using optical lattices. And that increases our gap sizes by about 3 orders of magnitude. So it makes it a little bit easier for us to get these states in the first place. Okay, and there is one last option. That's what I want to talk about at the end of today's talk, which is to apply a gauge potential which itself cools. Okay, so some type of dissipative gauge potential. And actually, we got into this game for the purposes of doing fractional quantum Hall physics, but we found out that there are some surprises along the way that led us to think about other things, like Yang-Mills and gravity. So I'll talk more about that later. Okay, so what is our scheme here? The basic idea is to take a superfluid gas and load it into an optical lattice. But we're going to make an optical lattice, which is, in a certain sense, an array of rotating optical buckets. So the way that we do that is we take 3 laser beams here. We form a two-dimensional lattice potential that looks like this. We translate that lattice potential rapidly, and the time average of that potential looks like an anisotropic harmonic oscillator, and we can make it spin around its own center. And of course, every lattice site in this sample is doing exactly the same thing. It's spinning around its own center. Okay? And if we add to that a one-dimensional standing wave, then we can chop up these tubes that we produce from this lattice structure like this into a stack of two-dimensional traps, which are all rotating. This is physically how we do it. We bring those 3 beams in with a single lens, and we have 2 electro-optic modulators that come in and allow us to move these traps along the plane. Okay. And so our final potential looks something like this. It's a 3D array of dot-like spinning few atom traps. Okay, and just for the experimentalists in the room, the harmonic oscillator frequencies are about 3 kilohertz by 30 kilohertz in this out of the plane direction. So it's a very tight two-dimensional trap. And we load atoms from a rubidium-87 Bose-Einstein condensate. Okay, everybody hear me okay? Okay. Okay, so there's some things that we need to do here. Actually, to get into the fractional quantum Hall regime, we have to be pretty precise with these traps, so we need to understand exactly what those lattice sites look like, so we can do things like crystallography here, which is just to allow the atoms, release them in time of flight, and then look at their interference pattern. So you can see these dots here telling you about the lattice structure. We can do similar types of things by pulsing the lattice on very quickly, and that produces time of flight patterns that look something like this. This tells you about the detailed structure inside of that lattice site. And so what's happening is basically all the atoms are collapsing to the bottom of the trap, and you're seeing the interference pattern after that has happened. Now, we can also cant the site, which is to say we can stretch the site along a particular direction, and we can measure relatively precisely how much we're able to make that site elliptical. So we understand those sites reasonably well this way. Actually, if you look in here, when those atoms fall down to the bottoms of the trap, they scatter off of each other, and so these are S-wave collision halos. We can also do things with single atom dynamics. So if we kick the traps, we can allow the atoms to oscillate in the center of mass for a very long time. This allows us to measure their trap frequencies and balance them, make them round to about 3 parts per thousand. Actually, when we do the actual experiments, we spend the bulk of our time doing this and maintaining the situation where our traps are round enough to be doing the spinning microtraps in a controlled way. Another thing that we can do is incite rotational instabilities in these spinning microtraps. So basically, if we take the rotation rate and we park it between the major and minor frequencies of the trap and rotate it, then we can actually get all the atoms to spin around the top, the lip of the trap. And this allows us to determine what this vibration frequency splitting is very precisely. Okay, so we understand that lattice structure pretty well. And we can actually do other things with it as well that have to do with the few body dynamics. So here we can look at the collective modes in the system. And so what we're doing here is taking the number of atoms per microtrap from 100 atoms all the way down to a single atom. And what we're looking at are the collective modes of the system. So here we're exciting the quadrupole mode of a two-dimensional gas of 10 down to 1 particle, and also the scissors mode. Now the scissors mode is kind of a distinct mode for superfluidity. And so this one is kind of interesting to look at as we go down into the single particle regime, where we're starting from a righteous superfluid with 100 atoms and taking it all the way down to the quantum pressure limited case of just a single atom. So if we look at what those look like, you can actually see that the scissors mode is actually damping out as you go into this dilute limit. Okay, and so you're seeing that you're going from a irrotational gas down to a rotational gas. We can do other things. For instance, we can take our superfluid and we can try to do a kind of classical nucleation of a vortex experiment. And so this is a pulse of rotation. What you're looking at is a series of pictures taken in time of flight after a short duration and increasing duration of rotation. What you can see is that the superfluid starts to respond by twisting itself. It's trying to form two vortices by the time it gets down here. But you can see that it's having trouble reconnecting those vortices. And the reason is that the harmonic oscillator length of the trap is comparable to the healing length of the superfluid. Okay, so we know that we're in the few body limit as well. But what we want to do is fractional quantum Hall physics. So how are we going to do that? It's helpful to look at how the spectrum of energy levels for a few body system works for this case. So if you think about what happens in a non-interacting gas in the lowest Landau level as a function of the frame rotation rate. Here I put it into the trap vibration frequency, units of the trap vibration frequency. What you can see is that as you get to the centrifugal limit, you have a macroscopic degeneracy, and this is the kind of thing that we want to exploit. Now if you turn on repulsive contact interactions, that's this part of the Hamiltonian, then what you see is that these correlated states, these ones with strong wave function overlap with zero angular momentum, are shifted up in energy. These other states that have higher amounts of angular momentum, there are ways for the atoms to correlate themselves with each other and reduce their repulsive interaction energy. And that allows us to introduce level crossings in this ground state sequence. And so what we can do is just apply a little bit of torque by deforming the trap, and that allows us to follow a ground state crossing down into one of these fractional quantum Hall states. So that's the basic scheme of what we're doing. I'm showing you here for 2 atoms. Of course, there are other pictures that I could draw for 3, 4, 5, up to 10 atoms or so is what we work with. Now, if I plot the energy gap between the lowest state and the first excited state in false color, it looks something like this. And what we actually want to do is, as a function of the trap deformation, this is how much we stretch the trap and the rotation rate, we want to follow some kind of adiabatic pathway into these fractional Hall states, like the Hecke-Laughlin state. Okay, so what can we look at after we do that kind of thing? Well, as a function of that final rotation rate, which is trying to deliver us into that fractional Hall state, we can just let the atoms go in time of flight and look at their density profile. And so here is a radial plot of their momentum distribution. Of course, we can decompose that into different components of the angular momentum from 0 up to 6. And if we compare that to what we would expect for fractional quantum Hall states using some numerics without any free parameters, but you can see that as a function of the final rotation rate of that trap, you can see that the 0 component of the angular momentum and also the first 2 components of the angular momentum follow your models pretty well. And this is this region in blue here is the range of the first ground state crossing for every occupancy of atoms from 2 to 6. Okay? We can also vary the mean occupancy of the atoms in the trap, and as we do that, we can see that it follows the numeric predictions reasonably well in that same region of the first ground state crossing for 2 to 6 atoms. Okay, another probe that we can do is to try to probe correlation in the sample. So one of those things about those wave functions that you notice is that they're very strongly correlated. They have 0 wave function overlap at short range. So a good way to probe that is to try to create molecules by shining on light which is resonant with a transition to an excited state molecule. What happens when we do this is called photoassociation. The excited state molecule very rapidly decays with enough kinetic energy that you lose the atoms from the trap. And so this is basically a way to probe the second order correlation function at short range. And if we apply that in our sample, what you can see is as a function of the final rotation rate, as we get closer to the centrifugal limit, we see that this photo association loss rate is strongly depressed. Okay? And actually, if we use what we had in the last slide, which is the time of flight momentum distribution, we can also take apart that wave function and try to calculate our best guess at the second order correlation function. And so here you see that correlation function evaluated in the center of the trap at z equals 0, and also at 1 harmonic oscillator length away from the center of the trap. And what we can see is that this follows pretty well with the forms that we would expect for the fractional quantum Hall states, which we write like this. This region with the first ground state crossing is essentially a crossing into the single vortex state. And so that's the one that we write like this. This has a fair amount of correlation in it, and so you can see that the second order correlation function is depressed. We actually get a little bit more depression than that, and we think that that's because we're actually following more ground state crossings into higher fractional quantum Hall states. And actually, if you try to figure out what the best that you could possibly do by following all of the ground state crossing sequences with perfect efficiency, you would get this orange box. These are error bars on our calculation. You can see that we're a little bit above that point. So we're certainly not making adiabatic crossings with all occupancies, but we're doing reasonably well. Another thing that we can do is try to make this crossing non-adiabatically. And so if we imagine that we have an adiabatic crossing in the ground state sequence, we go from a 0 angular momentum state to an n angular momentum state. We know that since we're always in an angular momentum eigenstate at the beginning and at the end, that we should have a round cloud. Now, on the other hand, if we go too fast, then we can create a diabatic splitting. And when we do that, we've got a superposition of 2 angular momentum states. Now, that is not round, and it also rotates along with the trap. And so what we can do is look at the cloud ellipticity for 2 different kinds of ramps, a fast one and a slow one. And we can look at how that cloud ellipticity follows with the final rotation rate. And what you can see is when we do slow ramps, adiabatic ramps, we have much less cloud ellipticity. When we do the fast ramps, we see that we can create this ellipticity, and we see that it follows the orientation of the trap at the point of release. Now, we can also use this to try to extract what our fidelity of crossing is. And so here you can see with the slow ramp, we have about a 4% peak ellipticity. And using our calculations, we see that this implies that that's about 5% population in the first excited state. So we've got about a 95% crossing fidelity into these single vortex states. Okay, so that is basically the status of the fractional Hall work. We are going in some new directions now. One of them is to try to introduce in situ microscopy for this. And so all of the data that I've showed you before is actually an ensemble measurement done on the entire sample of atoms in the gas. And actually, every lattice site that we load has a different number of atoms at it. So this is a pretty difficult thing for us to get past. So what we'd like to do is in situ microscopy, where we can actually resolve each one of these sites. Now, one of the things I didn't tell you before is that these sites are about 3.5 micron apart. So this is actually relatively easy for us to do. We don't have to get all the way down to half wavelength resolution. Another thing that we've thought about doing for looking at signatures for these states is to take those quantum Hall systems and allow them to just tunnel down the chain. And actually, this is kind of an interesting probe because what it does is it combines Mott insulator physics with fractional quantum Hall physics. And so a lot of you are familiar with phase diagrams that look a little bit like this for Bose-Hubbard systems with a plot of chemical potential and tunneling strength. You're used to seeing round Mott insulator lobes here with different occupancies. This is the phase diagram that we would expect for this system, which actually has insulating states. They're Mott insulating states, but they're Mott insulating states where the on-site wave function is actually a few-body fractional quantum Hall state. And just outside that, we have superfluids as well, which are mixtures of these angular momentum states. And these are kind of interesting types of superfluids because they're things that, in order to flow, have to twist. And they have interesting linkages between different properties. Their compressibility, for instance, is proportional to their moment of inertia. Their superfluid density is proportional to their torsional stiffness. So we think that this is a system which can give us a lot of new signatures and also allow us to produce very high fidelity fractional quantum Hall states by going into these insulating lobes. And then finally, I'm not going to talk about this very much, but we've also looked at signatures of fractional exchange statistics. And so we have a collaboration with Janendra Jain, which shows that there are ways of measuring fractional exchange statistics without actually getting in there and doing interferometry sequences. And this is basically to measure a fractionalized relative angular momentum between impurity atoms that are introduced into the droplets. Okay, but that's not what I want to talk about for the last half of the talk. Is it actually half of the talk? Good, great. Okay, so what I want to talk about is actually a new way of applying dissipative gauge potentials in order to try to create larger samples of fractional quantum Hall systems, but in a way which we're doing cooling continuously and at the same time trying to coax them into these fractional Hall states. And actually, this is something that we started in order to achieve that goal, but along the way we found some more interesting things. And so it's going to lead on a tangent that we didn't expect, and I apologize that it's not exactly in the fractional quantum Hall domain proper. But I want to go back to this question of gauge fields and why do we actually need a gauge field in the first place. Actually, if you think about it, what's going on in the fractional Hall states is that in a fluid, we actually only need to introduce angular momentum from some source. Whether we apply an external gauge field and what that gauge field is maybe not so important, but it's useful to coax the atoms into their own gaugeful state. So, you know, in a certain sense, we can always gauge in any interaction. We can think about any external interaction as a gauge field of some kind. Now, there is a non-trivial aspect of that, which is when their effect is not just another name for some type of mechanical force. And so there are a lot of cases here that we want to think about. One is that the gauge field stems from some kind of local symmetry in the system. Also, we want to think about what happens when the gauge field that we apply or that we create for the atoms becomes dynamical, which is to say that the gauge field itself is some kind of degree of freedom that interacts with the system. And thirdly, if the gauge field mediates interactions between the bodies, that's also a useful thing that we'd like to think about. And finally, if the counting of the gauge field equivalent configurations of this external body that we're using to apply a gauge field is changing, this can introduce non-trivial quantum effects. Okay? And all of these things, of course, we get bonus points if we can generate them with a non-abelian gauge potential. And so I'll show you that that's what we're working with in this case. Okay, so fluid vorticity obviously qualifies for these, but there's a downside to this, which is that it's a poor place to accumulate or dump entropy. So what we want to do is develop a dynamical gauge field which is capable of pumping entropy around in the system. So I want to do a simple warm-up for this, and it's based on the idea of dissipation being a form of quantum measurement. And so I want to imagine taking a spinful atom, and imagine that we make a measurement of the spin of the atom along a basis which is in the direction of the coordinate of the particle. So the measurement basis is going to be correlated with where the particle is. So if we just do that, if we measure a spin along a basis, along its radius vector, we get a 't-Hooft monopole structure, okay? Which is to say that we get a non-trivial gauge potential with a non-vanishing field curvature. Now, actually, this is kind of interesting because measuring, in a certain sense, is coupling and then forgetting. So you can imagine that we have an atom and an optical system. We're going to use the optical system to measure the spin of the atom along a position-dependent basis. After we couple the atom and the optical system together, in general, they're in an entangled state, and we can imagine that the measurement process is a form of projection, which eventually puts our system into some kind of density matrix form here. So we're taking an original quantum state and we're projecting it into a thermal state of some kind. Now also, if we started with a thermal state, we could imagine doing this process and maybe we can actually get it to dissipate or cool as well. Now there's another way of thinking about this. We can also take the environment or the apparatus that we're applying by shining light on the atoms, and we can think of that as a type of gauge field, which is to say that if we've got a Hamiltonian that involves the kinetic energy of the particles and then some kind of interaction Hamiltonian between the atoms and the optics, we can imagine taking this potential and gauging it into the kinetic energy of the atom. So now we can imagine that all of this complication of the atom-optical interaction, it comes in the form of a gauge potential like this. And now this gauge potential is a quantum operator, which is to say that it interacts with the atoms. And if we do that, we can imagine now integrating out the detailed state of the apparatus, which is to say that as we are spitting off photons, scattering photons off of this atom, we can just forget about where those photons went. And when we do that, we get a modified form of gauge field. And we also, this is a little bit of a subtle thing, but we also get a modified measure of the gauge field, which is to say that there are a certain number of gauge equivalent configurations, and that measure of how many equivalent configurations we have is changing. Okay, so what does that get us? One advantage of thinking about things this way is that the back action that we get from making a measurement is a continuous process. And so if we think about these gauge field dynamics as explaining the apparatus's behavior in a minimal way, then we can see that the entropy is indistinguishable from this idea of gauge equivalence, which is to say that if we're thinking about how this measure works, about how the number of states which are gauge equivalent is changing, we can actually associate that with the entropy that's carried out by the apparatus. Okay, so what are we doing here? In a certain sense, we're going from a picture where we have external gauge fields, where we apply a gauge field and tell an atom what to do with that gauge field. We have now introduced a way of thinking about dynamical gauge fields, which is to say, now we've put the gauge field and the atom into the same play box, and they play with one another. And What that means is that we've got a quantum mechanical gauge field which is now coupled to the atom's motion. Now, if you think about that, you can make an analogy to particle physics. A spinful particle's motion, actually in any complicated spin-dependent potential, can eventually be mapped onto an SU2 cross U1 electroweak interaction. This is a Yang-Mills model for its interaction. Basically, what this is telling us is that it's a transport equation. It's telling us that the current of the atoms is linked to the dynamical evolution of the gauge field. And of course, now that we've integrated out and forgot about how the light scattering process works, we have a non-vanishing field curvature in this equation. Okay, so this is just a simple or useful way of thinking about this kind of light-atom interaction. And it begs certain questions like, are there Higgs-like mechanisms? Okay, this is a Higgs-like model, so are there Higgs-like mechanisms? Do we have masses for the gauge bosons, and can we make them massless? Can we control the topology of a system like this? This is a little bit unlike particle physics where we don't have control over the topology of the system. And can we change phases in a way that might take us between cases where we have a Higgs-like mechanism and cases where we don't? Finally, can we use systems like this to shed light on difficult problems, like the connection between gauge fields and gravity? Okay? And I'm going to show you that we can, in a certain sense, see things that are like holographic effects. Okay? Now, I want to point out there's two other kids in this play box, and I don't know whose kids these are, and I thought about it for a little bit, and I realized that these kids are actually ghosts and gravitons. So there's a little bit more to that story in a minute. Okay, so there's one last hitch that I want to throw into this light scattering problem. And what I want to do is add something called a dark state effect. Okay, so this is basically the idea of rigging up the optical scattering so that we are coupling states inside the atom in a way which eventually leads us to a dark state. So we're going to pump atoms in a way, continuously scatter light until we get them into a state which is dark to the light. And actually, this adds a very non-trivial effect to this gauge formalism picture. In a certain sense, it adds new physics, which is that the gauge field dynamics are qualitatively different. It adds a new kind of gauge symmetry, which is essentially where did this atom come from once it arrived in this dark state. And it's also a practical constraint, because if we can use this dark state kind of picture, what we can do is make the excited state population of the atoms extremely low. So actually, we can make this as low as it is typically in experiments using very far off resonant light. And that's a neat trick for avoiding things like light-assisted collisions and photon recoils. Okay, so this is the experiment that I want to show you. Basically, what we do is we take very far off resonant light and we shine it in from multiple directions. But we do it in a way which has a lot of noise in it, which is to say we deliver that light through a very large diameter multimode fiber. This is a fiber that has about 10 to the 5 optical modes in it, and we have 4 fibers coming from the different directions. And so each of those creates a random polarization and random wavefront, which we shine down onto a region that's about 500 micron across inside the vacuum chamber. And this is where we put about 10 million rubidium-87 atoms at a temperature that's on the order of 100 nanokelvin. And then we arrange, actually there should be a beam that's coming through here. It's a little bit hard to see. This is a pumping beam. We arrange this pumping beam so that it rigs up a process, a dark state cooling process that looks something like this. There's a magnetic field that creates a Zeeman shift between the Zeeman levels and the F = 1 ground state. And we arrange it so that we've got this dark state in one of those Zeeman states. Now, I want to point out that we are lowering the scattering rate in this process to extremely low levels. This is not very typical for laser cooling, but we're actually scattering something like 1 photon a second when we're doing these experiments. So this is not a laser cooling experiment. This is really a very slow quantum dynamics kind of experiment. Now, to our surprise, we can actually continuously cool atoms in this potential for up to 20 minutes and still see that we're still cooling them. Obviously, there are background gas collisions that limit that to some extent, but we can actually keep this process going as long as we can keep people from coming in and out of the lab. And if you think about how this works, it's an atom-optical interaction that has, yes, kinetic energy for the atom, but it also has a conservative optical potential, as well as spin-dependent optical forces that come from polarization gradients from this random light. And then in addition to that, we also have real gravitational potential because the atoms actually sit on the planet Earth. Okay, so how can we use this to look at these kinds of phenomena? A very simple thing that we can do is just look at the non-equilibrium dynamics of atoms which are cooled in this very bumpy environment. And one of the consequences of the fact that we started from something that really didn't have gauge symmetry in the first place is that we would expect that our gauge bosons are massive, okay, which is to say they're like the W and Z particles. that they carry mass and they are unlike the photon, the gauge boson for the U1 symmetry. Okay, so how can we see this? Well, we can look at the slowest part of the non-equilibrium evolution of atoms in this system. And so here is the number of atoms that remain in our very noisy laser cooling system. You can see that if we apply heating or conservative potentials, we have an exponential decay of atoms from the system. But if we use this dark state cooling process, we can actually turn on a power law decay, and we can actually take this measurement out to about 2,000 seconds here and still see that we have a power law decay. Okay, so we have a scale invariant behavior of some kind in the non-equilibrium evolution. Now, if we actually take this dark state cooling and we turn its darkness up and down, so this is basically a measure of how dark that dark state cooling process is, what you can see is that there is a line of exponential decay here, which is indicating that we have some kind of massive gauge boson in all sectors of the problem. But once we get up to a certain point here, then all of a sudden we see power law decay for the rest of the range of darkness. And so what we can say is that we have basically turned on a masslessness in some sector of that gauge boson problem. Okay? So that dark state cooling has somehow invoked or turned off a Higgs mechanism, which is making our bosons massive. Okay, now we thought about this for a while, and actually one of the reasons that we got into it in the first place is that we were interested in the informational aspects of the problem. So we have a very disordered potential, and we start with a very hot gas. So the hot gas carries a lot of entropy, but the disordered potential carries a lot of information. And so if you think what's going on here, you're taking thermodynamic entropy and you're pumping the system into some kind of final state that carries information in it. And we thought that this was kind of an interesting problem from a classical kind of informational perspective. And actually, when we thought about it a little bit more and we thought about the quantum mechanics of it, we realized that it had a lot to do with gravity. Actually, this looks a little bit like the information paradox in black hole physics. So we thought about that a bit, and we came up with the following model. We said, let's take the atoms in this Hilbert space here, vibrational states and angular momentum internal levels, and let's take every state in this Hilbert space and let's put it somewhere on a plot. And then let's take the coupling between these states that happens because the atoms, say, tunnel from one well to the next, or flip a spin, or scatter a photon. And let's take the strength of the coupling and use that to stretch this plot and bring things that are coupled strongly together closer together, and things which are weakly coupled to each other farther apart. What you can reason is that atoms, as they are pumped into these dark states, will be pushed out into the convex regions of this plot. And so there's a certain kind of geometric aspect to this non-equilibrium physics as well. So we have these two kinds of things, informatic perspective and a geometric perspective, that are kind of hinting at gravitational physics. And I wouldn't say more about it than if it weren't for the following things. Actually, if you go into a detailed level and you actually figure out exactly how the quantum mechanics of a dynamical gauge field works, it's a tough problem, because actually what you have to do is very carefully count these gauge equivalent configurations. Actually, this is a long story that has to do with what are called Faddeev-Popov ghosts. These are ways of keeping track of how many gauge equivalent configurations you have in a quantum mechanics, a dynamical gauge problem. And actually, since our gauge field is emergent, the counting in this case is under our control, which is to say that we are able to control what's called the ghost dispersion, which is the energy versus momentum relationship for these ghosts that are determining how the dynamical gauge field evolves. Now, when there's a dark state, actually there's one more effect that we have to put in, which is the Unruh effect, which is to say that if we look at a vacuum mode of a system from an accelerated reference frame, we actually see it as a thermal body. Okay? And this is important when atoms get pumped into this dark state, because what's actually happening is that the only way for an atom to move from this locally dark state here to this locally dark state here is to move into a bright potential and eventually scatter light. And so in a certain sense, it is only because of fluctuations of the vacuum that we're able to move atoms around at the longest time scales in the first place. So these Unruh effects are important as well. Okay, all right. Okay, and so actually, there's one other trick that we have to do here, is that if we're going to remove these light scattering modes in a way that preserves the quantum mechanics of the problem, we also have to do it in a conformal way, which is to say that as we stretch the space and time scales, we want to make sure that we keep the problem conformally invariant. If we take these things and we put them together, conformal invariance is telling us that we have to have a certain number of degrees of freedom in the problem in order to keep the quantum mechanics valid. And there are special numbers for these degrees of freedom, 10, 11, 26. You might remember these kinds of things from things like string theory, which are telling us essentially how many conformal dimensions we need. The difference between these is whether we have things like supersymmetry or not. 26 is the one that doesn't involve supersymmetry, and so that's an important number to us. Okay, so here we can think that the degrees of freedom, in a certain sense, are the number of variables which are necessary to specify the local scattering states of the light. Okay? And so this is information that we actually provide to the atoms, and it's carried by the potential. Okay, so how can we quantify that? Well, we actually understand the modes in these optical fibers relatively well and how they propagate into the chamber. So we can take mode decompositions of these things and figure out what the electric field, the optical electric field, looks like inside the chamber. And if we do that, we can decompose them into singular values and look at a spectrum. We can use that to define how much information is in the potential in the first place. And so if we do that, depending on how we launch that fiber and how light is scattered along the length of that fiber, we can actually populate different amounts of K-space or different modes inside that fiber. And we can control how this scaling law of number of degrees of freedom in the potential per unit length goes. So this is how many degrees of freedom, how many variables are necessary to specify in order to understand the optical potential within a particular length scale. So here at 1 micron, for instance, we need something like 25 or so degrees of freedom to explain the potential. So we thought that that was interesting, and we wanted to look at one characteristic length scale, which is determined by the thermodynamics of the atoms. And so we did some microwave spectroscopy on the atoms to try to figure out what their temperature was. And we find that it's about 50, somewhere between 50 and 130 nanokelvin when we optimize the cooling. And if we look at what that means for our thermal de Broglie wavelength, what we see is that if we put that on our plot with the degrees of freedom, we see that we're in this range where we have about 26 degrees of freedom once the cooling reaches its equilibrium state. So we can think of this picture now as starting to explain a little bit about how this physics works. If we go inside that thermal de Broglie wavelength, what we expect is that the atomic wave function is dynamically correlated within that range, and it's only statistically correlated outside that range. If you compare that to what you would think about inside of a black hole, something like that, you have a causal horizon here, which prevents connections of things propagating across that causal horizon. And so you'd expect things to be dynamically correlated inside a black hole and only statistically correlated outside. So in a loose sense, we can think about that thermal de Broglie wavelength as being a sort of a killing horizon, okay, for a black hole. Okay, so what does this have to do with gravity? Actually, I thought nothing for a long time until I read a very interesting proposal by Eric Verlinde, which was that you can actually think of gravity in a certain sense as an entropic force. Okay? And this starts from a story that involves holography, which is to say that a particle, when it crosses a holographic boundary, stores bits of information as it goes inside. And so the number of bits that it stores is proportional to its area divided by some length scale, or some area scale, which in the case of gravitational physics is the Planck length scale. Now, if you put this together with a few other things, Planck area is given by the gravitational constant g. Add in the Unruh effect, and that the local acceleration, say on a horizon of a black hole or across any kind of holographic boundary, is proportional to its acceleration divided by the speed of light. You add into that the total energy of the system is this number of bits that we stored up here times some kind of thermal energy associated with that Unruh temperature. And we set that equal to the total amount of mass energy in the system, mc squared. And then we think about what happens as a particle crosses this boundary, how the entropy changes. We take all of these things and put them together, and there's a kind of miracle. I like to call it Verlinde's miracle, which is kind of like the Kaluza-Klein miracle, which is that if we look at the entropic force, treat the system kind of like a polymer with a spring constant, and think about how the free energy of the system changes as we add a particle across this horizon, what we find is we have exactly Newton's law for gravity. And actually that analogy goes much, much further. The extended miracle is that actually Einstein's equation of motion can be derived from the same kind of entropic argument. So actually gravity, in a certain sense, can be derived as an entropic force, and this idea of quantum dynamics coupling to thermodynamics is basically the underlying principle behind this idea. Okay, so if that's true, then we ought to be able to see holographic types of effects. And so one thing that we can try to do is vary this scaling law, which is to vary how many degrees of freedom we have per unit volume, and then see if these scaling relations, these power law decays of atoms in the potential, actually respond to this scaling. And what we find is that, yes, indeed, as we change the scaling of information in the potential, we see that the scaling, the power law, actually changes in a way that's linked to the amount of information in the potential. And so actually, if we take the amount of information in the potential, subtract 2 powers of the length scale, which is to say we take the information in potential per unit surface area, And we can see that it's equal to the dynamic critical exponent, which in this case is 1 times our number decay law. So actually, we can see that we can verify the holographic scaling laws in this problem as well. Okay, so I think with that, I'm pretty much out of time, and I'll just throw up a conclusion slide.
Question, Marcus.
Yeah, very interesting. If you go back a few steps,
Uh-huh,
so
yeah.
what's your, I mean, I guess this kind of system you're describing is very new to all of us. So we haven't thought much about how they know that it's behaving like I would expect it to behave,
Right.
or heating, all kind of different processes. Is that really the Hamiltonian? Can you say a bit more, just forgetting all the fancy implications?
Yeah,
Just
yeah.
The model itself. And also, are you in a regime there that's very hard to calculate, actually?
Yeah. So I left out a lot of the machinery behind the conclusions. The machinery is that we think of the light scattering process for the atoms as always being 2 photon processes. So for instance, spontaneous emission we think as being excited by a pumping beam, but then also excited down to the final state by the vacuum modes. And so we keep track of those vacuum modes, and we start from that Hamiltonian and basically gauge it away. Okay, so we apply a transformation to the wave function of the atom that takes that Hamiltonian and turns it into a gauge potential. That is a quantum mechanical operator. It operates on the vacuum modes of the scattered light. It operates also on the YAG potential as well, emitting and releasing photons. And so it's a quantum operator. Now, if we stop there, it would be kind of boring, because actually that is just a pure gauge transformation. Okay, so the curvature, for instance, doesn't vanish. The key step is that now we want to forget the detailed information about the scattered light. And so to do that, we integrate out those scattering modes. Okay? So what that does is basically creates a model which doesn't keep track of what modes have been scattered into, but only keeps track in a minimal way of how the atoms interact with the light.
Is it like pointer states kind of?
I'm not really sure what pointer state would mean.
Okay.
I mean, but one thing that is important here is that you are still keeping track of things like entropy. Okay, and this is a non-trivial fact, and it's.
And going back even a step, why doesn't just everything fly apart and get heated? And because that's what often happens, right? If you have cold clouds.
Well, no, because.
Where it's like on paper it all looks very nice, and then in reality.
Well, no, obviously we arrange for it to be a cooling scheme. Okay, and so in essence this looks like Raman sideband cooling, but it's an extremely disordered system. So it's not like the typical model that you're used to, where you're resonantly coupling states around, but they're all over the place. But as long as you bias it to cool, it will dissipate.
And why do you avoid collision?
We work at very low densities right now, but I will point out that the excited state. What's that?
Is it many body physics? Does the action matter?
We can do many body physics, and the reason is because the excited state fraction is so low. In fact, the YAG light creates more of an excited state fraction than our pumping light does. So we're basically just keeping up with the spontaneous scattering rate of the very far off resonant light by cooling.
Maybe one more question. Bert?
I didn't quite understand what you're measuring. When you're plotting the decay of something, what is it that's decaying, and why is it related to a quantum mechanical exponent in any way whatsoever?
Yeah, so I mean, basically what's happening is that we're locally pumping the atoms into dark states. Okay, so they're dark states and they're darker states. They can always tunnel though. And
the dark states are not part of your cloud in some sense.
well, they're optically dark.
Not interacting with the other.
They're not interacting with the light, but the atoms still can move in the potential. And actually, there's real gravity in the problem as well. So the atoms are always wanting to tunnel out of the system. And so by turning on the dissipation, we essentially arrest that process. Now the question is whether they leave in a way which is exponential in time, or a way which is power law in time, or scale invariant in time. And basically where the scale invariance comes from in a more classical perspective is that they're very slowly knocked out of this dark state. Okay? It's a quantum mechanical process. It basically requires a backward unitary process which absorbs a vacuum photon in order to get out of that state in the first place. And that's the only way that they can leave. So the scale invariance basically comes from that. That's one way of looking at the problem.
What does it have to do with a Higgs gap? I don't understand
Yeah, if you look at the dynamics of the problem, there's a transport equation, which is actually the Yang-Mills equation. And so if you want to ask what is the slowest process in this problem, it's related to what is the smallest energy gap in the problem. So if we have a massive gauge boson, then we have an exponential decay. But if we have a massless, gauge boson, then we have a scale invariant system, okay, or a power law decay.
I think it makes time to move on, but let's thank Nate again.